So, stoichiometry. I'm not going to go through all of this that's written here. We're going to talk about it, the important high points. We talked before last class about mole conversions and why the mole is important to letting us be able to quantify matter. We can use stoichiometric calculations to do pretty much anything and everything, and we will. So it's really important that we get the basics down while we're here in this unit. Balanced chemical equations are a must for stoichiometry. The big thing we need to know and that we need to get from our balanced equations is that it tells us what we have before and after a reaction, but we also are going to get the ratio of particles involved. Now, we're not going to ever really do reactions in a setting where you're going to be counting particles, right? But this is going to let us know the ratio of moles, which lets us know the ratio of masses, even though they're not related through a specific ratio, okay? Now, there's lots of different ways to do stoichiometry. I would guess that most of you learned stoichiometry using dimensional analysis, okay? Another method to perform stoichiometric calculations is the use of a BCA table, where B stands for before, C stands for change, and A stands for after. We're going to look at both of these methods. Okay? Have you used an ICE table before for equilibrium? It's the same method. It's just for a complete reaction. Okay? It's just a different way to organize your problems. I find it is, I don't know, for me, it really helps the way that my brain works. It also helps, you know, those really, really long Stoich problems where you have to find the limiting reactant, find the mass of product, find the mass of excess, find the percent yield, maybe even find the mass of the second product. A BCA table makes that less work, in my opinion. I'm going to show you both methods. I'm going to challenge you to try a different method just to see what you think. Because if it's different, you haven't done it, you're not going to know if you like it better, right? So we're going to look at just straight up Stoich, no limiting reactant with dimensional analysis. I got to go grab my notebook to make sure that I've got all my molar masses correct. Because I've been saying I'm going to be your molar mass machine today so that you don't have to do your molar masses. We're just going to save ourselves a little bit of time. Okay? So lithium hydroxide is used to remove exhaled carbon dioxide in space vehicles. Here's our balanced equation for what happens when that process takes place. Okay, so we don't have to have that piece. We've already got that balanced equation. You don't have to do that work. Okay. What we're looking for here is how many grams of carbon dioxide can be absorbed when 1 gram of lithium hydroxide reacts. So if we're going to solve this using dimensional analysis, we're going to start with that 1 gram of lithium hydroxide. And then we're going to need some more spaces. I like to set mine up first and then plug everything in, right? I want to go grams of lithium hydroxide into moles. I want to cancel moles of lithium hydroxide and convert to moles of CO2. And then I'll convert moles of CO2 into grams of CO2. This is just always how I do it. For me, for dimensional analysis, I like all the units first and then put the numbers in the right spots. Do you have to do it that way? No, don't care, as long as you do it right. Okay, so 1 mole of lithium hydroxide is 23.95 grams. 6.94 plus 16 plus 1.01. Okay. Mole ratio converts us from moles of one substance to moles of the other. This comes from our balanced equation. So I know for every 2 moles of lithium hydroxide that react, I will require 1 mole of carbon dioxide. And then 1 mole of carbon dioxide has a mass of 44.01 grams. I can cancel my units, make sure that everything works out, and then I can do the math. Right? We're going to take 1 divided by 23.95 divided by 2 times 44.01. Again, that's how I would do it. You can multiply across the top and the bottom and then divide. You do you. I do recommend, if you're going this method, do all your math at once. Don't stop along the way. There's more room for errors that way. How many significant figures should we report? 3, right? So what do we get? Great, 0.919. Whoops, that's the wrong color. 0.919 grams of CO2. Fantastic. Okay, simple Stoich. Okay, we're going to use the same reaction. We're going to use the same mass of lithium hydroxide. We're going to solve for product this time. And we're going to use a BCA table. Okay, let's take a look. Now, I like to color code when I'm looking through a problem. Anything I'm given, I like to highlight in one color. I use yellow. Anything I'm solving for, I highlight in pink. So in this case, I've got 1 gram of lithium hydroxide. We're looking for grams of solid lithium carbonate. I'm also told that I've got 1.17 grams of that lithium carbonate that are actually formed, and we want to know percent yield. So we're going to add a little bit in here. Okay. Now, what I want to do for my BCA table, I want to rewrite my equation over the top. Okay, so this is my same exact equation. We're just going to write it down again. 2 LiOH plus CO2 yields Li2CO3 plus water. Right? No. Yes, water. Why did I second guess myself? I'm going to throw my physical states in here as well. Water's a liquid, the lithium carbonate's a solid, CO2 is a gas, and the lithium hydroxide is a solid. If you're given information about physical states, include it. If you know information about physical states, include it, right? Like from your own experience. All right, now you got to make it into a table officially. Remember, B is before, C is change, A is after. I like to draw little lines to separate these into boxes. I'll draw a squiggly line or something a little different underneath the yield arrow as my cue while I'm working, as I'm going from reactants to products. This is particularly important when we get to equilibrium. We use ice tables because I see students a lot like just keep going with pluses and minuses all the way across their row instead of switching when you're consuming or forming. Okay? Now, if you've done an ice table before, what unit do you have to use in an ice table? Remember? It's not grams. Moles. Yeah? So we're also going to use moles in a BCA table. So we're going to convert into moles. We're going to work in moles. Okay? So we want to convert our 1 gram of lithium hydroxide into moles. Oop, I don't like that color. So moles of LiOH. I've got 1 gram. You can use this with dimensional analysis. Like I said, I'm showing you what I would do. We already used this molar mass. This is 23.95 grams per mole. Okay, now this is not going to be a final answer, so I don't want to round this all the way. I want to keep like what I would say is a reasonable number of significant figures. I think 4 or 5 is a pretty good number in a table like this. So I'm going to take it to 4, I think, is what I did. I did 4. This should be 0.04175 moles. Okay, so now that I have that, I'm going to put it in my table. What do we know about the amount of carbon dioxide from the problem? What are we told? Whoops. Excess, right? So we've got more than enough. So guess what? Excess. We don't really care how much we have in this particular case. We just know we have enough. How much product do we have to start out with? 0, yeah. No moles. We haven't formed any yet. So 0 moles, 0 moles, which makes it pretty easy for us with the change, right? If we don't have anything to start out with, we have to form it, which means we're going to be adding moles of product and consuming moles of reactants. Okay, so I also like to include the signs for the change before I do anything else. All right, if carbon dioxide is excess, we know we have to use all the lithium hydroxide. So we're going to subtract all the moles of lithium hydroxide. 0.04175 moles will be used. None's left over. All gone. How do I figure out how much carbon dioxide is needed? Well, that's our mole ratio, right? That's where this comes into play. So look at your equation. 2 moles of lithium hydroxide will require 1 mole of carbon dioxide. So if we know how many moles of lithium hydroxide react, what do I need to do to get the moles of CO2 that react? Take this number and divide by 2. Exactly. It's applying that mole ratio right here. Sometimes you can do it in your head, like know what you have to do. Sometimes you're going to want to do it in your calculator. Okay, let's divide this in half. We're going to get 0.02088 is what I'll call it here. Now, we don't know how much is left because we don't know how much we started with. So I'm still going to write excess. Okay. Look at the lithium carbonate in the water. We already should know how much change is occurring because 1 mole of CO2, 1 mole of lithium carbonate, 1 mole of water. Right? Their coefficients are the same, which means the change in the amount of substance will be the same. The difference is going to be carbon dioxide is used while our products are formed. See how that works? So we're going to go 0.02088 moles for each of these. Now, in this case, does the moles of water even matter to us? No, I just can't leave it blank because that would bother me. If you're good to leave it blank, that's fine. Because what we care about is the mass of lithium carbonate. Now we just go moles into grams using a molar mass, right? So let's do it. Let me change colors again. Ooh, I don't know what just happened there. 0.2088 moles. I don't think I wrote this molar mass down, so we'll do it together. 2 times 6.94 plus 12.01 plus 3 times 16 is 73.89 grams for every 1 mole. 89 grams for every 1 mole. What? What do you get? 1.54? Why are you being so shy? It's okay. Li2CO3. Are we done? Not yet. One more thing. Percent yield. You're given the actual yield in the problem. You either have to be given actual yield or you have to determine that in the lab setting. So it's 1.17 grams are actually formed. This is our theoretical yield. You're always going to find theoretical using Stoich. So, 1.17 grams over 1.54 grams times 100. 3 sig figs, I think is 76.0. I'm going to double check my math here. Yeah. Which is actually Pretty nice considering we've got a gas phase reactant. Okay, I would like you to please try the next one. I challenge you to use a BCA table if you haven't before. Okay, this one's a limiting reactant problem. You're given masses of both reactants. You're looking for the mass of the precipitate. You're looking for the grams of excess, and you're looking for percent yield. So, one thing I want to tell you about a BCA table is that when you're doing a limiting reactant problem, I find it's a foolproof way to find the correct limiting reactant. Because what happens is when you're applying your mole ratio in the change line, if you pick the wrong reactant as the limiting reactant, you're going to wind up with a negative answer for the after in the number of moles. And when you do that, you say, whoops, I picked the wrong one because I can't have negative moles, and you go back. So you're going to find out where that limiting reactant is sooner rather than later. When I was working through this problem on my own, I picked the wrong limiting reactant, but I wrote the wrong number of moles down. And it was pretty easy for me to go back and fix my work because I had to just erase a couple of things rather than go back and like redo all the dimensional analysis. Okay? So give it a shot, see how it goes, work together, check your answers with me if you finish before we're ready to go over it. Cool? All right, and I'm gonna continue my little recording real quick, even though I froze my screen, so that we can check our answer using the BCA table. With that,